Okay, so hello everyone. This is going to be the first lecture on the chapter 5 about Cartan decompositions and maximal compact subgroups. So the main idea here is that most of the preliminary work that we're going to need in order to develop the theory of Cartan decompositions was already done in chapter 3, where we studied the relationship between real forms of a complex semisimple Lie algebra and we saw that, well, these are obviously equivalent to real structures of a complex semisimple Lie algebra. And in chapter 3, we proved that there was a certain bijection between the set of real structures of a complex semisimple Lie algebra, which were the antilinear involutions, and the set of all involutive automorphisms of the complex semisimple Lie algebra. Okay. So the main idea is, again, to exploit these last equivalents in order to develop the Cartan decompositions for real semisimple Lie algebras. So let us start. Okay, so for our purposes, we're going to take a complex semisimple Lie algebra G. So let G be a complex semisimple Lie algebra. And assume that we are given a compact real structure. So remember that the the compact real forms of a complex semisimple Lie algebra were unique up to conjugation. So this compact real structure determines a compact real form, which is the fixed point set of tau. Which we're going to call U. Okay. So this is the starting framework. So now let's assume that we have an involutive automorphism that commutes with tau. Okay. So assume that theta is an involutive automorphism of G such that theta and tau commute. So if you remember from chapter 3, this this determines this new automorphism determines the isomorphism class of theta in the set of all anti-involutions, if I remember correctly. Okay, but what we're going to need here is to work with the fixed point set of theta, which is another. No, sorry. Theta is an involution, and tau is an anti-involution. So either of these compositions is going to be an anti-involution. So it's a real structure of G. Okay, so we're going to call sigma this anti-involution. And so it determines a real form, which we're going to call G0. Okay, so we wish to understand which is the effect that this automorphism theta has on the real semisimple the algebra G0. So the first thing that we should notice is that both real forms that we have described here, U and G0, are invariant under this automorphism theta. Okay. So this is a very simple computation, so I'm going to do it for G0, and the proof for you is going to be left for you to check, but it's essentially the same. Okay. So for example, if x is any element of G0, then theta x is in G0. So remember that being in G0 is the same as as being preserved by sigma. So theta x is going to be in G0 if and only if sigma of theta x is equal to theta x. So we simply have to check this condition. So sigma of theta x, by definition, is tau of theta x, but theta squared is the identity, so this is equal to tau x, and this is equal to theta x. And this last equality comes from the fact that x is equal to sigma of x, which is equal to tau of theta of x, right? So from x being equal to tau theta of x, one applies tau to both sides and deduces that tau x is equal to theta x, all right? So this proves that that really G0 is theta invariant. So yeah, the proof for U is similar, so I'm going to leave it for you to check. So that's an exercise. Okay. So again, we have these two real forms that are invariant under theta, and in particular, since theta is an involution, remember that it's going to be, as a linear map, is going to be diagonalizable with two eigenspaces for 1 and -1. So this is going to give us an eigenspace decomposition of the complex semisimple Lie algebra G, and therefore it's also going to give eigenspace decompositions for both G0 and U because of the invariance property. Okay. So since theta squared is the identity of G, it follows that G admits an eigenspace decomposition which I'm going to write as G equals G plus direct sum G minus, where G plus is the eigenspace of 1, or equivalently the fixed point set of theta, and G minus is the -1 eigenspace of theta. Right? So also remember that since theta is a Lie algebra involution, this eigenspace decomposition is a set to grading. That's something that we saw in the first chapter. Okay, but this decomposition is also true for theta thought of as a real linear map, and since U and G0 are real subspaces of G that are invariant under theta, this decomposition is going to restrict to both U and G0. So the decomposition can be restricted to U and G0. Okay, so we will write G0 equals G0 plus direct sum G0 minus, okay, where G0 plus is equal to G0 intersection G plus, and G0 minus is equal to G0 intersection G minus. And similarly for the compact real form U. Okay, so U is going to be equal to U plus intersection U minus with exactly the same notation as here above. All right. So for these eigenspaces, I'm going to select these first two, G0 plus and G0 minus, and I'm going to change their name to the more well-known notation of K and P for the Cartan decomposition of a symmetric space, for example. So from now on, we denote K to be the one eigenspace of theta in G0, and P to be equal to G0 minus. Okay. So the first thing that I wanted to do is to relate these two subspaces to the eigenspaces of theta for the compact real form, so for U plus and U minus. So I think I'm going to write it as an observation. So observation. Sorry. So note that in G0, the linear maps theta and tau are going to coincide. They have the same restriction. This is because G0 is the fixed point set of its composition. So from this, what we deduce is that K is equal to U plus, and P is not equal to U minus, but it's equal to I times U minus. Okay, so let's check these two equalities. They are very easy to prove from this observation. So proof. Okay, so I'm going to start by proving the first equality. K is equal to U plus. So let X be an element of K. Okay, so the fact that X is in K means that theta of X is equal to X, and also that sigma of X is equal to X. Okay, so this means that in particular, theta of X, which is equal to tau of X, is equal to X. So in particular, X is in the fixed point set of tau, which is precisely U. So it turns out that X has to be in U plus. So this proves one of the inclusions. The second one is essentially the same. If we have an element X in U plus, this means that tau of X is equal to X and theta of X is equal to X. So sigma of X, which is equal to theta of tau of X, is equal to theta of X because of X being in U, and this is equal to X because of X being in G plus. So this means that X is in G0 because sigma of X coincides with X, and it's also in G plus by definition, and this is equal to K. Okay, so far so good. I think this is more or less simple. And we also have the second equality, which is essentially the same. I don't know if you want to to also check it here, or if you feel comfortable having it as an exercise. So I don't know what you think.
I think
Okay.
you can skip the proof, yeah.
Yeah. Okay, I think it's more or less simple. So you just have to check that if x is in P, then I times x is in U minus, and the same for the other inclusion, so it's similar. Okay. Okay, so let's move on. So now I'm just simply going to rewrite these two decompositions in terms of these equalities. So we have these real subspaces of G0, K, and P, and the decompositions of G0 and U are now written as follows. So we obtain that G0 is equal to K plus P, and U is equal to, since U plus is K, so it's K here, and U minus is going to be I times P, so we have the relation U equal K times AP, right? These are not only eigenspace decompositions, it's very easy to check because of theta being a Lie algebra homomorphism, that both of these decompositions are set-to-set gradings. So note that these decompositions are set by to set gradings, in the sense that the Lie bracket of K with itself is contained in K. So K in particular is a Lie subalgebra of G0 and of U. The Lie bracket of K and P is contained in P, and the Lie bracket of P and P is contained in K. Okay. In particular, these inequalities imply that the decomposition of U is also set by two-set grading. All right. So this is the first ingredient. We now are going to define a second ingredient, which is a bilinear form induced by this decomposition that is going to turn out to be a scalar product. So in this sense, the real semisimple Lie algebra G0 is going to become an Euclidean vector space under this bilinear form. Okay. So remember that set by to set gradings are in a one-to-one correspondence with Lie algebra involutions. We're not going to need this for now, but I just wanted to remind this because giving the decomposition is going to later on be equivalent to giving a certain involution. So correspondence with Lie algebra involutions. This is something, again, that we saw on the first chapter. Okay, so let us take the killing form of the complex semisimple Lie algebra G, which we are going to denote by B. So let V be the killing form. Of G. Okay, so from it we're going to define this new bilinear form, which we will call B theta on G0 So we define a bilinear form B theta in G0. It's going to be taking values in the real numbers, and it takes x and y to minus b of x comma theta y. So if you're familiar with the theory of real semisimple Lie algebras, I think this bilinear form is not going to be very alien to you. So the first thing that we're going to check is that this, in fact, is a scalar product on G0. So I'm going to state it as a lemma. So B theta is an inner product on G0. Okay, so essentially the only thing that we need to check is that B theta is positive definite. But it turns out that we did a very similar computation in the third chapter by using these Hermitian forms on the complex semisimple Lie algebra G, which we called H tau for a compact real structure tau. And this turned out to be positive definite. And from it, we're going to deduce very quickly that indeed B theta is also positive definite. Okay, so proof. So we consider the Hermitian form H tau of xy to be equal to minus b of x comma theta y, tau y, sorry, where x and y are elements of G. So if I remember correctly, Thomas proved that this Hermitian form is positive definite in chapter 3. So this is positive definite. And remember that in G0, tau and theta are equal. So in particular, this Hermitian form has as its restriction to G0 precisely B theta. So this means that B theta is equal to H tau on G0. And so it's positive definite. Okay. So this is an inner product. And because of the expression of B theta on G0, it's very easy to see that this condition is equivalent to the Killing form being negative definite on K and positive definite in P. So it's an alternative way of expressing this condition. So this last condition is equivalent to the following two conditions. B being negative definite on K, and D being positive definite on P. Okay, so any set to grading of a real semisimple Lie algebra G0 satisfying these two conditions is going to be for us what we will call a Cartan decomposition. So I'm just going to write it here as a definition. So definition. Let G0 be a real semisimple Lie algebra. Any real semisimple Lie algebra. So a direct sum of G0 expressed as K plus P is called a Cartan decomposition if the killing form of G0, which note here that it's the restriction of the killing form of G to G0. So if the killing form of G0 is positive definite on P, and negative definite on K. Right? And as a consequence of what we have proved up to this moment, we deduce that this decomposition that we obtained for this real form G0 is a Cartan decomposition. Lagrange decomposition is indeed a Cartan decomposition. Okay. So far, let us just briefly recall what we have done. We have taken a complex semi-simple Lie algebra. We have taken a compact real structure and an evolution commuting with this compact real structure. And from it, we defined a specific real form of G0, and we proved that this G0 admits a Cartan decomposition and it's done as above. So the idea for me to do in the hopefully for the rest of this lecture, or maybe I'll need some time from the next lecture, is to prove that first, Cartan decompositions of the Cartan decomposition of a real semi-simple Lie algebra is unique up to inner automorphism, and secondly, that when we start with a real semi-simple Lie algebra G0, we can always find a Cartan decomposition, right? So the idea again is to keep playing with this relationship between these with this one-to-one correspondence between anti-involutions and involutions of complex semi-simple Lie algebras, and to always come back to the complexification of any real semi-simple Lie algebra. So let's start by the conjugacy problem. So conjugacy of Cartan decompositions. Okay, so the objective is to prove that any two Cartan decompositions of a given real semi-simple Lie algebra G0 are conjugate by inner automorphisms. So the first step in this improving this is to see that the process that we've done from the beginning is the only possible way to obtain Cartan decompositions. So all Cartan decompositions are going to come from compact real forms as K equals U and P equals I times U. As K equals U plus and P equals U minus I times U minus for some compact real form U. All right. So let's start from here. I think I'm going to be staying with this color. Okay, so suppose that we are given a Cartan decomposition. G0 equals K times P, where G0 is any real semisimple Lie algebra. And from the decomposition, we're going to construct the Cartan, the involution theta. Of G0 to itself by simply declaring that K and P are the 1 and -1 eigenspaces of theta. So theta at K is going to be equal to 1, and theta at P is going to be equal to -1. Okay, so this is a Lie algebra involution. I think Onishchik doesn't give the map theta any name, but we usually refer to theta as a Cartan involution. So Cartan decompositions and Cartan involutions are essentially the same thing, right? In the sense that in the same sense as compact real forms and compact real structures are the same, for example. Okay, so we're going to now take the complexification of G0, which is a complex semisimple Lie algebra. Okay, so let G be the complexification of G0, and we're going to let sigma be the conjugation with respect to G0. Conjugation with respect to G0. So it's a real structure. Okay. Also, while we define theta for G0, recall that theta can be extended to an involutive automorphism of G, as we saw in chapter 2. And I'm just going to be calling theta this automorphism, even though it's an extension. We denote by theta the extension of theta in G0. Okay. So note that we have now these two the real structure sigma and the involution theta, and these two commute, right? So note that theta sigma is equal to sigma theta, and this means that this composition is going to be a real structure that commutes with sigma. And the objective is to prove that this real structure is compact, all right? So tau equals theta sigma is a real structure commuting with sigma. So I claim that this is compact. Tau is a compact real structure. So in order to prove this is equivalent to proving that the Hermitian form H tau is positive definite. Again, we saw this in chapter 3, so we simply do it by direct computation. So if we take a generic element of G0 is of the form x plus y, where x is an element in K and y is an element in P. So if we take x in K and y in P, a generic element of G0 is x plus y. So we need to check that h tau of x plus y, comma, x plus y is greater than 0, right? So we proceed by definition. Who is h tau of x plus y, x plus y? This is minus the Killing form of g evaluated at x plus y and tau of x plus y. But since x plus y is an element of g0, tau and theta coincide. So this is equal to minus b of x plus y, theta of x plus y. Now, since x is in k, theta of x is equal to x, and since y is in p, theta of y is equal to minus y. So this is equal to minus b of x plus y, comma, x minus y. Therefore, this is simply minus b of x, comma, x, plus b of y, comma, y. Now, since x is in since x is in k, b is negative definite in k, so this number here is greater than 0. And since y is in p, this number is greater than 0. So this sum is greater than 0. Okay? This proves that h tau is positive definite on g0, but since g0 is a real form of g, this already proves that h tau is positive definite globally, right? So this proves that h tau is positive definite on g0, hence on g, right? So tau is compact, and therefore the associated real form is also compact, which I'm going to be calling U. So any questions so far?
No, it's okay.
Okay, so let's move on. So I want to work backwards. So remember that we proved when we went in the other way around from the beginning, we proved that U and G0 are invariant under theta. Now I need to prove that this compact real form is invariant under theta. Okay. So the real form U is theta invariant. Again, the proof is pretty much a one-liner, because if x is an element in U, then tau of theta x, if theta x is in U, then this must be equal to theta x. But tau of theta x is equal to theta sigma theta of x. But sigma and theta commute, so this is equal to sigma x. And this is equal to sigma theta of x, because of x being in U, so this is equal to theta x. So indeed, theta x is in U. Okay, so again, we have this involution theta. We have that U is a theta invariant subspace, so in particular we can restrict the eigenspace decomposition of theta to U, just as we did in the beginning. So theta of U is equal to U, and we get the decomposition U equals U plus direct sum U minus, right? So the idea is to see that K is indeed equal to U plus and P is equal to I times U minus. So we are left to prove that k, the given k is equal to u plus for this compact real form, and the p given is equal to I times u minus. So I'll just prove one of the two equalities. Again, these are going to be done by the same procedures that we have been using so far. So let's see that k is equal to u plus. So take any element x in u plus. We only need to see that sigma of x is equal to x. So we have sigma of x is equal to sigma of theta of x. This is because x is in u plus, and sigma theta is equal to tau of x, and this is equal to x because x is in u. So x is in g0, and it's in g0 plus by definition, and this is k. And again, if we have an element x in k, then we only have to prove that x is in u, or essentially that tau of x is equal to x. So tau of x is equal to tau of theta x. Tau theta is equal to sigma. So tau of x is equal to x, and this proves that x is in u plus. The other equality is essentially the same. So again, I'm leaving this to you as an exercise. Okay. Summarize what you said. Yeah. So to summarize everything that we've got, we arrived at the following theorem. Okay. To summarize, we have the following. So each Cartan decomposition of a real semisimple Lie algebra is of the form u plus plus I u minus for an adequate compact real form. Okay, so each Cartan decomposition of a real semisimple Lie algebra G0 is of the form G0 equals k plus p, where k is equal to u plus and p is equal to I u minus for some compact real form that is invariant under theta. So all of the Cartan decompositions of a real semisimple Lie algebra are obtained by the procedure that we described at the beginning of the lecture. Okay, so I think I have some 7 minutes approximately. So I'm going to start proving the theorem that any two Cartan decompositions of G0 are conjugate. Hopefully I can finish it in the time that we have, but if not, we will simply retake it in the next session.
I mean, if you want to finish it today, I have no problem. Yes.
Okay. Okay, it's not too long.
It
I
takes
think
a little bit more. It's maybe 5 or 10 minutes more.
No, but it's relatively short. So from this, it's going to follow quickly. So I think I have time. And I leave the existence problem for the next session. Okay. So as a consequence of this, we obtain that any two Cartan decompositions of G0 are conjugate by an inner automorphism. Of the real semisimple Lie algebra. Okay. So let's proceed with the proof. Okay. Take any two Cartan decompositions of G0. The first one is going to be called K plus P, and the second one is going to be called K1 plus P1. So to be Cartan decompositions of G0, and we take the complexification of G0 and we call it G. Again, we're going to define sigma to be the conjugation with respect to G0. And now we're going to take two compact real forms determined by the previous theorem, and we're going to think of the associated compact real structures, right? So let tau and tau1 be compact real structures commuting with sigma and determining the Cartan decompositions as in the previous theorem. As in the previous theorem. Okay, so I'm going to use a corollary that we saw on chapter 3. I don't have the book here, but I can give the reference later. But we have used this. We have used the result earlier. It's essentially that compact real forms are the compact real form is unique. So by a corollary from chapter 3, we can find an element psi in the group of inner automorphisms of the complex semisimple Lie algebra G, such that tau1 is equal to psi tau psi minus 1. And also psi sigma is equal to sigma psi, so both commute, because sigma commutes with tau and tau1. Again, this is because of the corollary. Okay. So because of these commutation relations, we deduce that G0 is invariant under psi. That psi of G0 is equal to G0, and also psi of the fixed point set of tau is equal to the fixed point set of tau1. All right? Or what's the same? psi of u is equal to u1, where u and u1 are the compact real forms determined by tau and tau1. Okay? So as a consequence of these relations, what do we get? We get that psi of k is equal to psi of u plus, but this is equal to u1 plus, and this is equal to k. So psi preserves k, sorry, k1, because it's the one eigenspace of u1. And psi of p is equal to psi of I u minus. This is going to be equal to I of u1 minus, and this is equal to p1 because of the definition of u1, u1. Okay, so if we prove that this inner automorphism psi restricts to G0, then we have finished the proof. Okay. So we only need to prove that psi, which is in principle an inner automorphism of G, restricts to an automorphism of G0. Okay, so the idea is the following. We come back to the corollary, and we may write psi in the following form. So from the construction of phi, we can write psi equals phi to 1 over 4, where phi t is a one-parameter subgroup of the group of inner automorphisms of G. So one-parameter subgroup of inner automorphisms of G. Okay, but because of semi-simplicity, this means that we may write phi to the t as e to t to add c, where this exponentiation is the usual the usual matrix exponential, all right? Some in G. So this comes from semi-simplicity and the fact that the Lie algebra of the group of inner automorphisms of the realification is out of G, all right? So we have these relations, and also that since sigma psi sigma equals psi, because sigma and psi commute, we get that the sigma of the e to the t at z, sigma is equal to e to the t at c for all t. So now we can differentiate this equation and take the derivative at t equals 0. And we obtain that sigma at c sigma is equal to at c. Okay. But since sigma is an anti-homomorphism of the algebras, this is equal to add of sigma c. Okay? So this means that since add is injective, because we're working with semisimple the algebras, that sigma of c is equal to c. So c is an element of G0. So this already implies that psi is going to restrict to G0 because add c already restricts to G0, and so does the exponential. So therefore, psi restricts to G0 and is therefore the element of the inner automorphism group that we're looking for. And this proves the conjugacy of Cartan decompositions. So in a sense, they are unique. So I think I'm going to leave it for now. And in the next session, we will discuss briefly the existence of a Cartan decomposition. We will see the example of SL and C, and to see all the Cartan decompositions for the real forms of SL and C, and we will start working on the multiplicative Cartan decompositions for the automorphism group. So that's all for today.
Nice.
I don't know if you have any questions for.
Well, I have one. Why do you think this 1/4 appears usually in this kind of the algebra stuff?
I think it's simply because
it's an open question, but not a...
So the short answer is I don't know, and I don't dare to give an attempt at an explanation. I think I don't know. It appeared on chapter 3 for because it was necessary at the time, and I can't really tell if there is an ulterior motive for 1/4 being a magical number appearing in the theory of the algebras and inner automorphisms.
Okay.
So, this was the. I think I have the. Yeah, I have the notes here by the book itself, because the corollary of what I was mentioning is in chapter 3, and let's see if I can find it.
Yeah, because I think it's going to appear even later, this 1/4 again.
Yeah, it's proposition 6, essentially. So in proposition 6, I don't remember the proof of these propositions. I only remember the result. And the reason that they take t equals a 1/4 or minus 1/4 is that they want some operators to coincide, and these coincide exactly when 4t is equal to -1. So I don't know if that answers your question. It simply appears as.
Yeah, I see.
Yes, it was just solving the equations. You wrote that in some particular way, this automorphism. You check that in order to mute, I think, with tau or whatever it was, have to tau for there. So it's because of that.
Yeah, but I was thinking that maybe could be related also with the fact that there are some important classes of Riemannian manifolds which are 1/4 pinch, like the complex projective space is 1/4 pinch, the quaternion projective space is 1/4 pinch, the Cayley projective, indeed, all the rank 1 symmetric spaces are 1/4 pinch, and sometimes this is a very rigid condition, like under certain hypotheses, if you have a Riemannian manifold who has this 1/4 pinching in the curvature, then if you put some more hypotheses, you get a rank 1 symmetric space or one of these, yeah. And maybe it could be related with that. I don't know why it's always this 4. Maybe there's no relation at all, but at the moment I thought about that, or it recalled me that stuff.
Mm-hmm. Okay, so I don't know if you have any more comments or questions or on what was done here. I think it's more or less easier than the previous chapters for now. This is going to be pretty lightweight in comparison to the previous chapters, I think.
Yeah, but maybe also because we are very used to work with this stuff. So.
Yeah, this is well known for us, but
okay.